Welcome to EDU World Space.
For this problem, we have a sign that is being supported by a beam here that's attached to a pivot point here, and then there is a cable that supports the beam and keeps it from rotating about this point here. The one attachment point for the sign is a distance d from the pivot point, and the sign has a width here of 2L. There is obviously a reaction force from the cable, and we can assume that the weight, because the sign is in rotational equilibrium, these two forces have to be equal, and they have to be half of the weight. So we have half of the weight acting on this cable and half the weight acting on this cable. And then we have reaction forces at the pivot point here. And so we're not given any values, but they ask us to solve for these things symbolically. So we can take moments about point A, and doing that we find that we have a moment from the tension in the cable and moments from the weight of the sign. This actually allows us to solve directly for T, and doing so we wind up with, after some simplification, we show that T is proportional to W. Okay, so the greater the sign weighs, the greater this tension will be proportionally. T varies with the cosecant of this angle, so 1 over the sine. So if this angle goes to 0, we're in trouble here because this tension would have to go to infinity. And obviously, if we can make this angle greater, then the tension would drop. And then we also have a relationship with a ratio of these lengths. So a ratio of d plus L to d plus 2L. So if say d got very small compared to L, then we would just have a 1/2 out here. Or say L was very small compared to D, then we would just have a 1 here. And if we use force balances, we can find these reaction forces. So in the vertical direction we have this equation, and in the horizontal direction this equation. And again, we can see that the forces at the pivot point here are both proportional to W, the weight of the sign. This force has the same coefficient here concerning the lengths. And now it depends on the cotangent of theta. So that's the cosine theta over the sine of theta. So again, we can see that it would go to infinity as theta goes to 0, and we're better off having larger angles here. And then we can figure out what f of y is, and we find out that that actually is independent of that angle. And this factor out here, again, is proportional to the weight of the sign, and the factor concerning the lengths is L over D plus 2L. So again, if L gets large compared to D, then this gets to be 1/2. If D is large compared to L, well, then we just get L over D here, and we can't really simplify this anymore. This just overwhelms this, so we can neglect that, but then we wind up with D over L, and there's nothing we can do about that. There's no simplification there, other than that if D is very much larger than L, then this would be a small number, and then this would be a small number also.